All right. So, hold on. Let me double check something because I think something just messed up. All right. So today we are going to be continuing on from predicting single replacement reactions to predicting double replacement reactions. So yesterday we had the activity series. That was the thing that I passed out at the beginning of class. That's for you to keep for your notes. On the test, you are not likely to have to do a single replacement. But for me, just in good conscience, I have to teach you the single replacement. So before I start teaching today, I want to make sure that you have all of your active stuff off and all of that stuff off. Also, I'd like for you to make sure that you don't have any earbuds in or things like that. Because if my administrator walks in here, I get in trouble, not necessarily you. But ultimately, it comes back to that. All right. So, today we're going to be looking at double replacement reactions. We're predicting those products. We're going to also see how to determine if something is soluble or insoluble. We are not going to get to the net ionic and complete ionic equations today. That will be tomorrow. All right. So, looking at double replacement reactions. The way that we predict products for double replacement reactions is different than single replacement. So yesterday, all the stuff that we did yesterday only applies to when you have a single element and a compound together. What we're going to be doing today is only double replacement. So I'm going to give you some kind of foundations, some vocabulary, and some rules first, and then we'll get into the practicing of it. All right. So in a double replacement reaction, in order to predict products, all of the reactants should be ionic compounds. So if the reactants are not ionic compounds, then we can't really predict the products. We would have to do the experiment and see what's made. But if they're all ionic compounds, then we can predict the products because we can do the crisscross and all of that to see what's going to happen. Second statement, the products in a double replacement reaction are formed by switching the cations. The positive ions are going to trade partners. But in order to write our new compounds, our new products, we have to use that little crisscross rule because we have to determine the new ratio of elements based on the charges of those two elements. So not only are our reactants ionic, our products should be ionic as well, are based off of ionic rules. And then the last kind of rule to be able to predict a double replacement reaction, the reactants have to be aqueous. All right. Both reactants will be aqueous in this, meaning that they're ionic compounds dissolved in water. All right. Now, there are going to be some terms that we need to know in relation to aqueous solutions. So the first off, anytime you see, let me go back to that slide on here because it's not going to show up on mine. Anytime you see the word solution, that tells us, so saying aqueous solution is kind of like a redundant statement. So when we say solution, we're going to assume aqueous. All right. That's like saying GPS system. The S already stands for system. All right. So now we need some vocabulary that we're going to associate with the word aqueous. Remember that aqueous means dissolved in water. All right. The first term that I want us to associate with aqueous is the term soluble. Soluble means that it will dissolve in a liquid. What liquid do you think is the primary liquid that we're going to be dissolving things in? Water. So we will always be dissolving in water. Water is known as the universal solvent because given enough time, water can dissolve just about anything. Doesn't dissolve everything well, but it will dissolve most things. All right. The other thing is anytime that we see something as soluble, when we're writing it in a compound, if it's a soluble compound, we're going to say that it's aqueous. All right. So soluble means that it will dissolve. That means it's going to form an aqueous solution. The other term that I need us to know is insoluble. Insoluble does not dissolve. So if I add something that's insoluble to water, what phase of matter is that substance going to be? Solid. So insoluble will be solid. Soluble dissolves in the liquid. Insoluble does not dissolve. Insoluble is going to remain a solid. Hot water. All right. And just to clarify, an aqueous solution is a homogeneous mixture of a substance and water. This one's been out of the window. All right, does anybody need more time on this slide? Okay. Remind myself. Oh, sorry, I had one more statement on there anyway. All right. So when we put an ionic compound, a soluble ionic compound in water, the ionic compound separates into its ions. The water molecules kind of get in between and pushes the ions apart. So they separate all that. I'll demonstrate that on the next slide just so that we can kind of see what's going on. Bless you. All right. So that word disassociate just means to break apart or separate. So when we're looking at soluble ionic compounds in water, they're going to break up into their ions. So if I have my most common ionic compound example, which is sodium chloride, when I put that in a container of water, it's going to become a sodium ion, and a chlorine ion. If I were to put potassium phosphate, which is another soluble ionic compound in water, it's going to separate into 3 potassium ions and 1 phosphate ion. So kind of looking at this graphically or in a picture form, if I have my little cup of water here and I have a spoonful of NaCl, I pour some of that NaCl in there. When it gets into the water, it's going to start forming these ions of chlorine ions, sodium ions, and so on. But there's always going to be an equal number of sodium and chlorine, all right, because NaCl is a 1-to-1 ratio. With potassium phosphate, on the other hand, so I've got my spoonful of whenever this one breaks apart, for every 1 phosphate, I'm going to have 3 potassium ions. So, ooh, that's a bad choice.
It's all right.
I didn't even notice that. I can change that to sodium. All right. I'll change that to sodium in the future. I didn't even, because I've never drawn it like that before, so it never hit me. All right. No, well, it's actually on recording, so, but, all right, that is not what that's intended to be. All right, because that kind of shocked me. All right, so how do we determine if something is soluble or insoluble? We have to use these solubility tables. So what I'd like for you to do is go ahead, take out your periodic table reference packet, and we're going to go back and we're going to look at how do we use these things. So I'm going to go through the rules on these first and kind of explain what these rules mean. So you need your periodic table reference packet. It is on the second page, I believe, down in the bottom right-hand corner. You'll find these. All right. So notice that one of these talks about compounds that are mostly soluble. And then the other one talks about ions that are mostly insoluble. So I want to look at the rules and explain how these work for each table. All right. So in regard to the periodic table, what do lithium, sodium, and potassium have in common? Specifically, in regard to the periodic table, what do lithium, sodium, and potassium have in common? They are all alkaline. They are all group 1A. They're all +1. But specifically, they're all in the same family on the periodic table. So the table doesn't list every one of these, but everything in group 1A is always soluble. So Group 1A elements, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, are always soluble. All right. Another cation, another polyatomic ion, positive polyatomic ion, that is always soluble is ammonium, which is NH4 plus 1. All right. So if you see a compound containing any one of those things, it's always soluble. So you know, if I had lithium chloride, or I don't know, no, that should be a 2. If I had rubidium sulfate, lithium chloride, I should immediately know that both of those are going to be aqueous. Why should I immediately know that those are going to be aqueous? They're both alkaline metals. So rubidium and lithium are both alkaline metals, so they fall into that category. All right. Now, the second grouping of elements that are always soluble is compounds that contain nitrate or acetate. So if I have something like, I don't know, let's see, lead to acetate. So acetate is this C2H3O2. And if it's lead 2 acetate, it's going to take 3 of these to offset one lead 3. But because this is here, that's going to be aqueous. All right. If I have lead 2 nitrate, lead 2 nitrate will always be aqueous because nitrates are always aqueous. All right. Now, getting into where they actually start having some exceptions. So notice for both of those categories, it says there's no exceptions. They are always soluble. Now we're starting to get into exceptions. So chlorine, bromine, and iodine, they are all halogens, but I'm not going to make a general statement about the group of halogens because fluorine has some situations where it's not going to follow all the same rules. But when I look at chlorine, bromine, and iodine, fluorine is always soluble, whereas chlorine, bromine, and iodine are not. Chlorine, bromine, and iodine are always soluble except when bonded with silver, mercury, or lead. If you have a compound containing silver, mercury, or lead and a chlorine, bromine, or iodine, so if I have PbI2, that's going to be solid because it's insoluble. Whereas magnesium iodide will be aqueous. All right. So notice how, because it contained lead, that makes the iodine insoluble. But if it has anything other than silver, lead, or mercury, it's soluble. And then the last grouping is sulfate. Sulfate is always soluble except when it's paired with calcium, strontium, barium, or lead. So looking at that rules about things that are always soluble, do you see a problem element that would make us kind of go look at that chart? What's an element that tends to make things insoluble? Lead. So if I see compounds containing lead, I'm going to go look at the rules and make sure it's soluble or insoluble. If I see something that's from that group 1A column, I'm going to automatically know that it's aqueous. If I see ammonium, I'm going to know it's aqueous. If I see nitrate, I'm going to know it's aqueous. All right, I'm not going to even go back to the chart. So the only reason why I go to the charts is when it's one of those that I just don't know off the top of my head. All right, now, things that make things insoluble. So we're going to start looking at this list and looking at the exceptions. All right. So everything on this list is insoluble except when the conditions apply. So hydroxide and sulfur, OH negative and sulfide are always, compounds containing those are always going to be insoluble except when bonded with a group 1 metal or ammonium. All right. So if it's bonded with a group 1 metal or ammonium, that makes it soluble. Anything else, it's insoluble. When sulfur combines with calcium, strontium, barium, it's soluble. When hydroxide combines with calcium, strontium, or barium, it says it's considered slightly soluble. We're going to treat slightly soluble as soluble. All right, so when we see that condition, we're going to treat it as soluble. And then the last two, carbonate and phosphate, we'll treat those as insoluble unless it's a group 1 metal or ammonium. All right, so if we see it with a group 1 metal or ammonium. So let's look at these up top. So I'm going to point out some things that should make it easy for us to figure out. So in these two, so for A, aluminum nitrate, what's the rule about nitrate? Always soluble. There's no exception. So anytime we see nitrate, so if it's soluble, I'm going to write AQ. If it's insoluble, I'm going to write S. All right. So nitrate makes it always soluble. So aluminum nitrate, lead nitrate is always soluble. Why would I have been given pause on this one before I wrote aqueous? Because of the lead. So I just wanted to make sure I verify that lead with that is still soluble. All right. Now, the next two are not as easy because they're chloride. So we have to make sure of some specifics on those. So chlorine, bromine, and iodine are always soluble except when silver, mercury, or lead are applied. So in this one, magnesium, is that silver, mercury, or lead? No, so that's aqueous. All right. Zinc, is that silver, mercury, or lead? No, that's aqueous. Most of the time, we're going to end up with things that are aqueous in the reactions that we're going to be seeing. There's only going to be a few that end up being insoluble. Now, there are going to be some intentional insoluble ones, especially on this practice that we're doing. So now, I want you to take a minute, and I want you to go through and determine which ones you think are soluble and insoluble, and why. Yes? So let's start looking at a couple of these. All right, I want us to look at C, K, and N first. I underlined rubidium, sodium, and ammonium. And I always try to get rid of the easy ones first, the ones that I can know without really thinking. What do rubidium and sodium have in common? They're both alkaline metals. They're both group 1A. So what do we know about 1A? Always aqueous. So these, I don't really have to think about whether that's soluble or insoluble. Because of its location, I know it's aqueous. All right, ammonium. Did we have a rule for ammonium? Well, first off, we need to know that NH4 plus is ammonium. That's one of the few positive polyatomic ions. So what's the rule for ammonium? It's always soluble. So I'm going to put AQ. Now, for the rest of these, I put circles around lead because lead's a problem child for me. I didn't see mercury or silver listed anywhere on here, so that one's not really a problem child for me. All right, so going through here, let's start with nickel hydroxide. Do I have any rules that apply to nickel? No. Do I have any rules that apply to hydroxide? All right, so it says that hydroxide is always insoluble except with group 1 metals, calcium, strontium, or barium. So should this be solid or aqueous? Solid, because hydroxide is always solid, insoluble, except for those things. And those things don't meet nickel. What about magnesium hydroxide? It's insoluble, so we're going to call it solid. I'm skipping the, I don't know why I circled iron. I didn't mean to circle iron. All right. Notice I'm skipping the leads for right now because we're going to treat those separately. All right. What about iron 3 phosphate? Do I have any rules about iron? No. Do I have any rules about phosphate? Insoluble except lithium, sodium, potassium, ammonium. So it's solid. Let's go ahead. Cobalt 3 sulfide. Do I have any rules about sulfide? Well, first off, what is sulfide? This is sulfide. All right. So when I look there, does cobalt meet any of the exceptions for sulfide? No. So we're going to say insoluble. All right. Carbonate. Do I have any rules for carbonate? Does magnesium meet the exception for carbonate? No. So that means it's solid. All right. So now we're left with our problem children. Lead 2 sulfide and lead 2 sulfate. All right. Lead's one that I recognize is most of the time lead's going to be insoluble. All right. And then I'm looking, I have lead 2 with sulfur. So both of those are mostly insoluble, so I don't really have to think about that one being insoluble. And then I have lead 2 with sulfate. So I do have a rule about sulfate being mostly soluble, and then, but I have the exception that with lead, it's insoluble. All right. So it's going to be to your advantage to kind of get familiar with these charts. I'm not telling you to memorize these charts or anything like that, but get familiar and practice with using them. the way the questions are going to be asked in active, it's going to give you a set of 2 compounds, and it wants you to create the products, and it's going to ask, is one of these a precipitate? Or is it going to form a precipitate, or is it not? If it says if it's a precipitate, that means it's a solid, it's insoluble. Not precipitate means everything's aqueous. All right, so just kind of keep in mind there. So one of the things that I want us to know is acids are always soluble. When you think about an acid, what element do all acids have in common? Hydrogen. So you're always going to have some formula, hydrogen with some other anion, right? And that's going to make our acid. Notice where hydrogen is listed on the periodic table. It's listed with group 1A. So that automatically hits our rule that group 1A elements are always soluble. All right. Soluble compounds are going to be written as aqueous. Soluble compounds are considered to be electrolytes. That means they conduct electricity. Electrolytes are very important for biological processes. That's why, like, if you're in sports or doing any kind of physically strenuous activities, they typically tell you to drink lots of fluids, and sometimes they will tell you to drink things like Pedialyte, Gatorade, Powerade, all of that, because they contain electrolytes that replenish those salts that we sweat out. Those ions in our blood and those ions in and around our muscles are very important for electrical conductivity, because our nervous system is electrical. And if we don't have enough ions, our brain can't signal our muscles to function properly. So if you've ever been dehydrated, you know your body just doesn't move like it's supposed to move. And that's when injuries occur. All right. Insoluble compounds are considered to be non-electrolytes, which means they don't conduct electricity, or they're poor conductors. Insoluble compounds are going to tend to be solids when you put them in water. All right. So when we talk about electrolytes, you're also going to hear sometimes salts is a term that they put with electrolytes. Soluble ionic compounds are considered to be electrolytes. And I'll say that again. Soluble ionic compounds are considered to be electrolytes. Soluble ionic compounds are referred to as a class of compounds called salts. All right. And so if I take regular table salt, dissolve it in water, remember it's going to form a sodium ion and a chlorine ion. In our bodies, those salts, those electrolytes, are in ion form because most of our body, the majority of the mass of our body is water, H2O. So they're going to stay in ion form, and that's what allows the conductivity in our muscles and all of our, really all of our nervous system reactions. All right. Yes. Yes, you can. All right. So now putting all of this information that we did, putting it in relation to a double replacement reaction. How do we know if a double replacement reaction is going to occur? A double replacement reaction will occur, or we say it goes to completion if a solid, liquid, or gas forms. All right. Now, when we're writing these compounds, in order to determine if something is a solid, it has to be on the solubility table. That's we look at those rules. We figure out if that's going to form a solid or aqueous solution. Liquid, the only liquid we will tend to deal with as a product of a double replacement reaction is water. And then gases, some of the things that we react may produce hydrogen gas, chlorine gas, carbon dioxide's another one that we may get. But those are kind of it for the gases. There's not going to be many gases. And usually when it's a gas, I'll tell you that it's a gas. I can't, it's not going to be something I expect you to immediately know. All right. If we do a double replacement reaction and all of the products end up being aqueous, just like yesterday, whenever the compound ion was higher, we said no reaction. Same thing we would refer to in this. If all the products end up being aqueous, if your reactants are aqueous and your products are aqueous, then we're not going to see a visible reaction. So there may be a reaction that occurs, but we can't tell that it occurred because everything's still ions. All right, so one more definition, and then we're going to do some practice with these. All right. The last definition I need you to know is a precipitation reaction and the term precipitate. So if we do a reaction and a solid forms, that's called a precipitation reaction. The solid itself is called a precipitate. And the word precipitation and precipitate just basically means that it falls out. So if you think about the atmosphere and we talk about precipitation, we're talking about something falling from the sky, either liquid water or solid water in the form of snow or sleet or hail. So precipitate reactions or precipitation reactions, a solid is formed during the reaction and it's going to precipitate out. It's going to fall out. All right. So when I pull up the next slide, I want you to copy down the reaction. I have it written in two places on the screen. Just one's bigger. So I have it written like a prompt that you would have to predict the products. So when I pull it up, I want you to predict the products, and then we're going to go through and talk about why things are what they are. All right, does anybody need more time on this slide? All right, so go ahead, write this down on your paper. I want you to predict the products, and we're going to see if a reaction occurs or not in this one. Yes. Yes. if you're having trouble knowing what goes with what, so like the outers are going to go with each other, so sodium and hydroxide, and the inners, calcium and carbonate, are going to go with each other when you're creating your product. All right. Now, remember, to get your new formulas, you're going to have to use crisscross methods, so you have to compare the charges because these are ionic compounds. So when I look at these, calcium is now going to react with carbonate. Notice that the charge on calcium is a +2. The charge with carbonate is a -2. So when those react, they're equal and opposite charges, so they'll react 1 to 1. Notice with sodium, it's a +1, hydroxide's a -1. They're also going to react 1 to 1. But over here, they didn't, so that means we're going to have to balance this at the end. So for calcium carbonate, I should write CaCO3. For sodium hydroxide, I'm going to write NaOH. Now, let's look at sodium hydroxide first. Why do I know that sodium hydroxide is aqueous? Sodium is a group 1. Sodium's always aqueous. And then calcium carbonate, I needed to look that up. All right? So calcium, I'm going to look up. I don't see anything specific about calcium, but I do see something specific about carbonate. And carbonate says that it is insoluble unless it's bonded with a group 1 metal. So that's why I know that one is solid. In the active problems, you can get this right, you can get this right, and you can balance it correctly. If you don't put the phases of matter in active when it asks you to write it out, it's going to mark it wrong. If you put the wrong phase of matter, it's going to mark it wrong. Now, to balance this, all I have to do is put a 2 in front of NaOH, and that balances it. So when we do these in active, it's looking for you to complete all of these steps. All right. Now, I'm kind of helping you out because I'm putting the ions on top of it because I want you to realize they're there. But I want you to go ahead and try these two, and we'll discuss what they would look like in active as well. So go ahead, write these two down, and we'll discuss the answers in just a minute. It's the same problems. I just did it on a different screen. All right. So starting to look at these. Ammonium is now going to partner with chlorine, and calcium is now going to partner with carbonate. So ammonium and chlorine are 1-to-1, so it's going to be NH4Cl. Calcium and carbonate is calcium's a +2, carbonate's a -2, so it's going to be a 1-to-1 reaction. So it's going to be CaCO3. In either of those two, ammonium with chlorine or calcium with carbonate, will either one of those form a solid? If so, which one? CaCO3 is going to be our solid. All right. So this is our precipitate. The solid is our precipitate. That's what makes this a precipitation reaction. That's also going to be what allows us to visibly see the reaction occur. We'll know that something happened because we see that solid forming. All right. On this next one, calcium is now going to be bonded with iodine. Sorry, potassium is now going to be bonded with iodine, and calcium is now going to be bonded with nitrate. Notice that I always put the metal first in the compound. Don't flip them around. Potassium and iodine are both 1s, +1, -1. So that means they're going to react 1-to-1. And then calcium is a +2, nitrate is a -2, -1. So it's going to take 2 nitrates to offset the 1 calcium when we write our formula. But looking at those two, calcium with iodine, will that be aqueous or not? It's going to be aqueous. Potassium with iodine, that will be aqueous. Calcium with nitrate, will that be aqueous or solid? Aqueous. So when we do this one, both things end up being aqueous. So if I poured 2 liquids together and everything stays aqueous, the reactants and the products, am I going to see any change? No. So in this case, instead of writing this, if it were on active, we would write no reaction because we can't see it happen. The only way that we can know for sure that a reaction occurred there, and there will be some reaction occurs. There will be some Ki made. There will be some calcium nitrate made. But the only way that we'll ever see that happen is if we evaporate all the water off. And even then, we may not be able to tell because if all the crystals are white, we can't distinguish one white crystal from another. All right. The only way we might know is if one of the crystals are blue or green or something like that. All right. Kind of last thing before I end up today. Acid-base reactions. Acid-base reactions are reactions that form water upon mixing an acid and a base. So an acid-base reaction, remember we identified an acid as always having hydrogen in it as the beginning element, and we identified a base as always having hydroxide in it. the products of an acid-base reaction will always be water and a salt. Remember, a salt is a soluble ionic compound, not just table salt. It will be a salt. All right. We call these types of reactions, we call these neutralization reactions. They're just a special type of double replacement. So you can see this still fits the pattern of double replacement, especially if I write this as HOH rather than H2O. So it still fits the pattern of double replacement, and we call it neutralization because we're neutralizing the acid. Instead of having a low pH like an acid and a high pH like a base, we now have a neutral pH of 7 because nothing is acidic or basic in it anymore. All right. Water always gets the liquid symbol to it. It's not because you can't dissolve water in water. Water is just water. All right. And so if we look at another scenario where I have sulfuric acid plus potassium hydroxide, both of those are aqueous. And then our products, we produce water and potassium sulfate. Our potassium sulfate is the soluble ionic salt. And so if you would take out that sheet that we had that I gave you yesterday that was numbered like 1 through 8, 1 through 13, whatever it was, 1 through 12. All right. I'm not gonna do this one in class, but I'm gonna do these two in class. I'm not gonna do the third one in class. But if you'll circle number 5 and number 6, these are both double replacement reactions. Also, number 12 is a double replacement reaction that you could have done, that you can do on your own later, and just see if you still get it. All right. So take a minute. I want you to try these on your own, see what you get, and then we'll go from there. All right, so let's look at number 3 together real quick. So silver nitrate is aqueous. It's going to be AgNO3. Zinc chloride, remember zinc's always a +2, so it's going to be ZnCl2. And that is aqueous as well. When we trade the partners, silver's new partner is going to be chlorine. Silver's always a +1, so it's going to be AgCl. And then the other new partner is going to be zinc nitrate 3. Now, I have to look it up and see, is there anything that we know for sure is going to be aqueous in this product? The nitrate is always aqueous. So there should be a 2 there, by the way. All right. Now, I have to look up AgCl. When I look up the rules for Cl, Cl is aqueous except when silver, lead, or mercury. So that means that is my solid. So we will see that reaction occur because of that solid there. All right, coming through on this one. We'll start with sodium. Sodium gets a new partner of sulfate. Sulfate's got a -2 charge, so that means it's going to be Na2SO4. Now, as far as aqueous or not, what do we know about sodium? It's always soluble, so it's always going to be aqueous. Now, hydrogen in this case is going to react with hydroxide, which I'm going to write it like this for now, but you should recognize it as something else. So H2O, what will H2O be? Liquid. All right. Now, I didn't balance these. So let's go through and balance this. In order to balance this one, I need 2 sodiums. So I'll put a 2 there. When I do that, I need 2 hydroxides. So I'll put a 2 there, and it balances. Silver nitrate, silver's balanced, chlorine's not. So I need to put a 2 here and a 2 there. Yes.
Explain how you got the 2 on Na, like sodium. Bottom right. Like,
look up sulfate in your when you look up sulfate as a polyatomic ion, it has a -2 charge. No. Chlorine is a group 7A, so it's a -1. So in that one, and then in this one, OH negative. All right. So the questions that I'm adding to our active problems. All right. So just kind of going through, summarizing yesterday and today. For single replacement reactions, we use that activity series. That's how we know if the reaction is going to occur or not. For double replacement reactions, we have to use the solubility, and it only happens if a solid, liquid, or gas produces. All right. I've already assigned problems 1 through 4, 20 through 27, and 29 through 36. The new problems that you can begin working with is problems 5 through 10 and 17 through 19. Problems 11 through 16 are what we're covering tomorrow. All right. Number 37, you can probably do. You just need to pay attention to what it tells you. Write out the entire expression and then balance it correctly. It's not necessarily a balancing one that just jumps out at you.